All right, so let's do a quick op-amp circuits example problem, and then we will be done with this module. So I'm going to go ahead and draw ground here. Make this a 10K resistor. We'll make this let's make this a 50K resistor. All right. And then this will be V out of T. And we want to determine V out of T in the following circuit. Okay. So you can either recognize that this is a non-inverting amplifier and just use the formula, or I can go through and derive it myself by using the KCL at that node again, and that's what I'm going to do just because that's the long way to do it. But feel free, if you recognize these topologies, to just use equations that we've already derived. So I'm going to go ahead and call this again IR1 of T, and then this one will be IR2 of T. And we know from KCL at this node, of course, that IR1 of T is going to be equal to IR2 of T, since no current flows into the op-amp terminal, right? That current's 0. And so all we have to do is write these out. Let me go ahead and give us a VS, though. Let's say VS of T is going to be equal to 2 times the sine of 2 pi times 1K times T volts. Okay? So all we have to do here is, I would leave everything in terms of Vs of T and Vo of T until the end, just to make the math easier. But we could, of course, write this as a phasor if we want. So we could write it as Vs is equal to is equal to 2 angle 0 degrees volts. And if we really wanted to, we could rewrite the op-amp in terms of its impedances rather than its resistances. But because they're just resistors, right, we could probably just ignore that step and save ourselves some time. But I'll just draw the equivalent circuit anyways. So this one would be a 10K impedance, this would be a 50K impedance, and we basically have the exact same circuit, where my V out now is just going to be a phasor, and we just saw that my Vs is 2 angle 0, right? So anyways, if I were to write the current across the 10K, I would write, and note, there's something important to note here, that because these two terminals, again, are the same, this node is no longer 0 voltage. This node is going to have this voltage appear at that node, okay? So let's go ahead and write it out. We've basically got, across the 10K, we've got IR1, which is going to be 0 on the left, right? I'm writing the voltage across it this way. I've got 0 volts on the left, minus the voltage at the minus terminal of the op-amp, which has to be equal to the voltage at the plus terminal of the op-amp. So it's actually Vs of T. So this is going to be Vs of T divided by 10K, right? And now if I want to go the voltage across the 50K, right, that's going to be going this way. I'm going to have Vs of T minus V out of T divided by 50K. All right, and so my goal was to solve for V out of T. So let's go ahead and do that. But we kind of, I don't want to run out of room here, so let me shrink some of this stuff. All right, so that can be made much smaller. And then from here, I would basically just separate terms. I would say minus Vs of T over 10K. I would subtract this Vs of T over 50K over to the other side. And then I would be left with a minus V out of T over 50K. And so I can multiply both sides by negative 50K here. And I would get that this goes to Vs over T times 5, right? 50 over 10. Or I guess, yeah. And then on the other side, or right here, I just get another Vs of T. And then right here, I just get V out of T. And so I basically get that V out of T is going to be equal to 6 times Vs of t, right? Skipped a lot of steps mathematically there, but basically I just moved terms around and isolated V out of t. And what we can see, again, just like we would expect, is that we got V out equal to V in multiplied by 1 plus R2 over R1, exactly like we should expect from a non-inverting op-amp configuration. Okay, so that's going to be my op-amp circuit example, and I am going to go ahead and wrap up this module with that. So we're officially done recording module 1. I'm super excited to say that, and we're going to go ahead and move on to module 2 from here, which is frequency response and filter circuits. Okay, so I'm going to go ahead and end this video.